Hello and welcome to another video, and in this one we're going to focus on adding reflections to our ray tracer and abstracting our code a little bit more. So let's get started. So as you see here, this we'll try to get an end result like this with multiple spheres and triangles and rendering in our ray tracer and the reflections they cast, making an interesting scene. I'm just going to close this out as it'll just be like too intensive to be running in the background. But in order to get there, we're going to first get to this step, and then eventually we'll just add more to our scene. So close this out too. Currently, this is where we left off last time. So let's get to working towards our end result. Right. So jumping back into our code. First, I'm going to modify our triangles so they look closer to how we wanted the end. And for that, we're going to change this so it goes -1 to the left and -1 up. And then change this z to 0. Change this z to 0 as well. And then we want to go -1 to the left and -1 up. And then here, we want to go -1 to the left. And we want to go -2 in z. So let's go take a look at what that does. Perfect. That's kind of what we're going for. And now let's go back and do the same for the red triangle on the right. So if we go right here, we're gonna go, this is good. We're just gonna zero out the Z. And here we're gonna make this positive because we wanna go -1 to the right. That's it. And here we'll make this 0 as well. Now let's take a look at if we're able to get what we want. Yes, that looks good. Now let's go back to our scene. The next thing to do is we're going to be adding reflections. So we want to add that piece to our triangles and spheres. So right after the diffuse shader, we're going to add reflectivity where we can control how reflective we want the object to be. I'm going to put it on 0.75 because that's a pretty good number that will yield what we want at the end. So I'm going to just go ahead and do that for our triangles. There we go. Now we need to do the same for our sphere as well. And I'm going to go with um, 0.5 on here. And you'll kind of see at the end, I feel like these are good numbers for what we're trying to achieve. So now that we got the reflectivity, variable added, next thing to do is let's go down. We need to go down to our code. We need to make things a little bit more abstract. And the first thing to do is in our calculate color function, we're going to go here instead of um, doing array to color here, we're going to take this off and we're just going to call send the color. And when we come here, we're going to do array to color. We're going to call it here. And this should just not, change much. Yeah, it should work just fine. Let's go back to our code. Then another thing I would like to do is go back to our calculate color function and this part where we do if result then continue, which is for otherwise the calculations contribution of this light source. So what we're going to do is we're going to comment this out. This will be better. There we go. That's kind of what we're going for when we're trying to go for these reflections. So we're going to go ahead and comment that out because we want to get that result and work with it for our reflections. The next thing to do is to cast a ray and compute the color at the intersection point. So we're going to make a new function and this will help abstract our code a little bit more and help with calculating our reflection. So right above our render function, I'm going to go ahead and make a function called cast color. In here, we're going to have our O, origin of the ray, and R, direction of the ray, and then remaining bounces. And this will be the number of remaining reflection bounces. And what we're going to do is, first, we're going to check if remaining bounces equals 0. If so, then return 0, 0, 0. So if we're basically saying stop recursion if no bounces are left. So then we return black. Then we go, if there is bounces, then we go, we call it result, or we're setting our variable result, and it'll be cast array, and we're gonna call it here. It's gonna be O. We're gonna pass in the O origin of the array and R direction of the array. And basically, we're saying cast array and find the nearest intersection. Next line, we're gonna go and say if does not equal result, then return black. Alright, so we're saying return black if no intersection is found. If there is intersection found, then return calculate color, then result, comma, remaining bounces. So we're saying calculate the color at the intersection point. And since we're passing in remaining bounces there, we need to go add that parameter to our calculate color function. Once we do that, we should go down here. Now our thing should be a lot simpler. We're gonna say color here. And then we should just be able to remove this section of the code. Remove this if statement as well, because you have moved it to a function. And I believe just go array to color, pass in the color. We're gonna remove this, and hopefully it just works. No, we have an issue. Let's see. Console reading cannot read property 0. Okay, let's see. All right. So the issue is now that you have kind of changed, abstracted, and moved it to a function, I'm still calling cast array. Instead, we need to be calling our new function cast color. So where we call our cast array usually in our render function, we need to instead go ahead and call cast color. And then after we pass in the origin of the array and the direction of the array, we need to pass in the remaining bounces. So I'm just gonna go with 1 right now, and let's hopefully go back and our code just works. Yep, that's great. And I'm gonna make these, the triangles on the side, the green and red, into white, as it'll be better for when once we get to adding reflections. So let's scroll up where we do our setup. In our setup, we're just gonna make this one. All right, let's go take a look. All right, great. Now we have that set up. And the next thing I'm gonna do is I'm gonna change the color of our checker shader. Currently, we just have it as uh, yellow and black. Instead, I'm gonna go with blue because I think it just produces a much better scene. So we're gonna go blue instead of yellow, and then instead of doing black, we're gonna do like a lighter blue. Let's go take a look. All right, perfect. So the next step is to calculate reflections. So to do that, first we're gonna go to our cast array function, and at the very end, where we pass in our nearest p, nearest distance, and our nearest spec, I want to pass in r as well because we're gonna need that uh, to calculate our reflections. So, and then we're going to go back up to our calculate color function. In here, we need to do a little setup for our reflective light. So right after we get our arriving light here, I want to do initialize a reflective light contribution. So I want to let reflective light equal, and then just set it up to 0. Perfect. So then I'm gonna do a little comment here. Let's go down here. This is where I'm gonna do calculate reflections. Okay. So in order to do that, what we're gonna do is here we get our color. Instead, it's gonna be the final diffuse color. And what this is gonna do is gonna combine diffuse and reflective light. So we get the final diffuse color, um, which currently it combines arriving light with the object's diffuse color. Next, we're gonna go here. We're gonna do let color equal add, and then we're gonna do two things that we're gonna add. We need to first scale them. So we're gonna call our scale function, and in here we're gonna pass in the final diffuse color, and we're gonna scale it by 1 minus the reflectivity, which we need to get, which we need to initialize, which I'm going to do in a second. Then the second thing we add with is we're going to call the scale function again. And here we pass in the reflective light that we had initialized. So we go reflective light, comma, R, and we scale it by the reflectivity of the object. So I'm going to go up here where I did this comment, and we're going to get the reflectivity of the object. So we're going to do let R equal result dot spec dot reflectivity. So this gets the reflectivity of the object. The scale is 0 to 1, 0 being no reflection and 1 being full reflection. And what we have chosen for our triangles is 0.75, which is closer to full reflection, and for the sphere 0.5, so it's in between of full and no reflection. So now let's take a look at our scene. So this is how it looks right now. So not much reflection going on. So let's do the calculation for that. Currently our reflective light is just, just empty, black. So let's go ahead and do that by first having an if statement where we check if the reflectivity is not 0. Small case r, keep that in mind. And if it's not, which means we do have reflection, then I'm going to let reflective vector equal, this is where the calculation that Dr. Ricks uh, wrote up comes into play. So we're going to, this line right here computes the reflection vector. And it reflects the ray direction around the normal. So we're going to do minus, we already did, we're going to use the minus function. And what we're going to do is we're going to get results dot r. Remember when we we just added that to the end of the cast ray function. We use that. Then we scale by n normal, and then we scale that by 2 times dot product of n comma result dot r. Next, we're gonna do is get the reflection origin. So we're going to let reflection origin equal add. We use the add function, pass in our p, and then scale. The next thing we're going to add with the p is the scaled reflection vector. spell it right, vector, and we're gonna scale it by really small value like point 0.0000001. So what this one is doing is it's offsetting the reflection origin slightly. And the next line is gonna be the reflection color. So we're gonna do let reflection color equal, we're gonna call the cast color function. And what this is doing is recursively cast the reflection ray. And for this, we're gonna pass in the reflection origin, reflection vector, and the remaining bounce is -1. So we keep reducing each time, and we recursively cast the reflection ray. Finally, we set reflective light to what we get from the reflection color call. And with that, let's take a look at what we get. Reflection, let's see, reflection color, no, it's having reflection vector, okay, oh, I misspelled it, reflection vector, reflection vector, okay, let's see, alright, that's not, we're not quite there yet. So now that we have done the code for calculating reflections, currently we're just doing one bounce. So now to actually see the reflection like we want, we need to add in more bounces. So let's go to increase it to something like 5. And now let's take a look. There we go. That's what we're going for right there. You can see the reflection of um, the sphere on the triangle and vice versa. So the next thing to do is you can kind of see there's um, like jagged edges here. It's called aliasing, and we're gonna do a little bit of. We have seen this in Blender, where the amount of samples you take, the more you take, the smoother and nicer it looks, and the lesser it is, it looks all jagged and stuff when you render the image. So we're gonna implement our own little, um, not necessarily the best way, but a quick and dirty way of doing anti-aliasing. So let's begin by going to our render function here. This is where we're going to do that uh, calculation. So at the beginning, we're going to set a variable for the amount of samples per pixel that we're going to take for in order to do the anti-aliasing. So currently, I'm just going to put it at something like 2 because the more and more you take, that many times it needs to do it, and it's going to increase the render time, making things really complex. And then next thing is, currently we have 2 loops. We're going to have to add a third one. So but before we add that third one, we need to initialize an array called SumColor, and this will be the accumulated color for that pixel. So we're going to let SumColor equal, we're just gonna, initialize it. Then we're gonna make our third for loop. In here, we're gonna do let I equals 0, I is less than samples, and then I plus plus. And then I'm going to take that and move it over here. Then I'm going to indent all the stuff that we have inside this for loop. Perfect. So the next thing to do is we call let color equals cast color. We do that. After that, we're going to do some color equals add some color color. So basically, we're gonna take this color and we're gonna add it with the some color, and we're gonna accumulate the color. Then this section right here, where we um, draw the pixel, we're gonna do that outside. So we're gonna go right here, and basically, what we're gonna do is currently we just do array. We call the array to color function and pass in the color. Instead, we're gonna take this. We're gonna do scale function. First, we pass in the sum color, and we scale it by 1 over the amount of samples. And so what we're doing here is we're average the accumulated color and draw the pixel. And this line right here, it scales the color by the number of samples. So let's go see what happens to our scene. Nothing much should have really changed, but the next thing to do is we need to add these two key functions. So let's go up to where we, do our like helper functions. Right below where we do array to color, we're gonna make a function called small random. So we're gonna do function small random. We're gonna pass in delta. So basically, this will generate a small random value within the range from negative delta to delta, and delta is the maximum absolute value of the random offset. And with this, we're gonna return a random value in the range of negative delta to delta. We're gonna do that by returning bracket math dot random function, and we're going to multiply that by 2 minus 1, and that's going to be multiplied by delta. So it generates a random number in the array 0, comma 1, and scale to negative 1, comma 1, multiplied by delta. And then we need another function. This one's going to be called jitter. And in here we pass in v and delta. And basically what this function does is add a small random jitter to a vector. And v is the input vector to jitter, and delta is the maximum magnitude of the jitter, and it'll return the jittered and normalized vector. And so what we're going to have here is a return straight up. And this first we'll call the normalized function. In here we're going to call the add function. After that, we pass in v. And the second thing that we pass in is an array with small random passed in delta. Now we do this 3 more times. So I'm gonna go small random delta again, pass in delta, small random, and pass in delta. So what this function is effectively doing is it's normalizing the resulting vector to maintain its direction. So we pass in v, which is the input vector to jitter, and then we're gonna pass in the maximum. So you have v is the array, and then the number delta is the maximum magnitude of the jitter. We get that, and then we call normalize, and then inside that we call the add function, where we first pass in the v. Then the pass in 3, we call small random delta 3 times in an array. This to add a small random offset to each component of the vector. So random offset for the x component, that's this. Then random offset for the y component, and then random offset for the z component. So now that we have implemented our small random and jitter functions, let's go ahead and use it. So let's go to our render function. And in here, where we pass in our r, we're going to call the jitter function. Then pass in the r to it, we're in the v parameter. Then we pass in for the number, it'll be 0.001. So this add jitter for the anti-aliasing, and it'll allow up to 5 bounces. That's what's happening in this sentence. So let's go to our here. Still a little bit, you can see. So, because we still need to call it in one more place, and that is in our calculate color function. So let's go up here and right here. So where we do our reflection vector, computing the reflection vector, where it reflects the ray direction around the normal, we need to add a small random jitter to this reflection vector for anti-aliasing. So outside of the minus function we're going to go ahead and call the jitter function, and where the v parameter goes, that's where the result of the minus function goes, and then we're just going to provide the 0.1 for the small jitter, and let's see what this does. Okay, that looks pretty good, and what we can do now is increase our sample count to something like 16, and now we should get a good looking render, but it's going to take longer because of the amount of samples we're taking, 16 times. So let's give it a second, and there we go. That looks great. You if you zoom in, you'll probably see that little bit of aliasing, but when you look at it like this, it looks great with the anti-aliasing we have implemented. So we're done with all that. So now we can just make the scene a little bit more interesting by adding a couple spheres and triangles so we can achieve what I showed at the beginning of the video. So let's go to where we do our setup right here. First, let's add another sphere. So I'm going to copy this right here, put it right there. I'm going to make this the z for both of this -2. Goes a little bit away from us. And then I want to make this smaller, 0.5 for the radius. And then I'm going to push this one to the left, so negative 0.5, and push this to the right, 0.5. I'm going to make this sphere spec 2, and we're going to need to call it in our spheres array, so it gets rendered. And now let's go take a look. It's going to take a while, so what we're going to do here, once this is rendered, I'm going to show a little quick thing that it's a better way when you're kind of adding and messing around with the scene, is to turn down the sample count. Ooh, that's not quite ideal. Okay, might have messed something up. 0.5. It looks good. Oh, I did 1.5. That's the issue. All right. But yeah, let's go ahead and do one more thing down here. So this kind of applies to in Blender as well, which is when you're working in the viewport and you're messing around, you want things to quickly render and not slow you down. So you want to have the sample count low. But then when you go to rendering, that's when you have the sample counts as high as you would like, because you just do that one time. But then for this, you don't want to constantly do that. That's going to take away from your time of developing. So perfect, we got that. Now let's add two more spheres, one at the top and one at the bottom. So let's go back here where we do our setup, and I'm gonna just copy. I think I already have a copy. No? Yes, there we go. Yep. And then we're gonna do -2. Make this 0.5 as well. 0.5. And this one, I'm gonna do the top one first. So I'm just gonna do 0.85. Go up, and copy this real quick. There we go. Sphere spec. Call this 4. We're gonna make this one go down. 0.5. Make sure we call it in here so you see it. Sphere spec 4. There we go. Perfect. Let's go take a look at our scene. Hopefully this renders quicker. Perfect. We got our spheres. Now we need to render our triangles, that top and bottom. So for that, I'm gonna just quickly copy this. Actually, copy both of this because we need two more triangles. Put this here, 3 and 4, and we're gonna make new ones, 3 and 4. And I'm not gonna put those in there just yet because I'm gonna set this up first. So I'm just gonna go ahead and copy this triangle right here, paste this twice. This is gonna be 3. This is gonna be 4. 4. There we go. So I want this one to go -1 to the left and 1 up, then 1 to the right and 1 up, and 1.25 up from just the 0. That's great. So let's go ahead and take a look at this triangle. Triangles back 3. Alright. Hopefully it just runs quicker. Perfect. That's what we want. Now let's go ahead and set up our triangle 4. For this, what I want is I want it to go -1 to the left and -0.8 up, and then I want it to go zero point 0.8 up. Wait, this one is zero point 0.8, -0.8 down. This one also -0.8 down, but then I want to go 1 to the right and then down. Here, just want to stay at the origin, but I want to go -1.25 down. And then we just have our z of -2, and hopefully this should get us what we would like. Just go ahead and hit a refresh. Oh, there you go. Silly mistake. I did not call the triangle. I did not put it in our triangles list. Let's see. Great. So for the final render, now we can go ahead and go back to our 16 samples and take a look at it, and hopefully it should look all nice with the reflections, much more complex scene, and with the anti-aliasing, so we don't have those jagged edges. So let's there we go. There we go. Now it has loaded, and that looks great. So before we wrap it up, I'm just gonna quickly go over what we had done in this video. So first, the main thing that we did was do the reflection, implement the reflection. So the reflection logic, right? Let's quickly go over that. So let's go to our calculate color function. Here, this is where we do it. So the reflection vector is computed by reflecting the ray direction around the surface normal, and then we add a small jitter to the reflection vector to reduce the aliasing and create smoother reflections, as you can see in the final render. Then the reflection rays recursively cast using the cast color function that we implemented, and the reflected light is combined with the diffuse light. And the diffuse and reflective light combination that happens here is the diffuse light is scaled by 1 minus the reflectivity of the object, and the reflective light is scaled by the reflectivity of the object. And this way we can, our final color we get is a weighted combination of diffuse and reflective contributions. Then we implemented anti-aliasing, which is down here, where we're taking multiple samples per pixel by jittering the ray direction slightly, and the colors from all the samples are averaged to produce a smoother image. Get that right here. And um, we're doing recursive reflections and using the remaining bounces parameter, which will limit the amount of times we recurse, so that way we're not infinite looping. And then finally, we have um, our helper functions that we made, which is the small random and jitter functions, which help us with the anti-aliasing. So that's it for this video. Thank you for watching.